I have maybe one on, one off.
Sacha, do you want?
Yeah.
All right.
Yeah.
We'll switch.
Okay.
Presenting.
Okay, here.
Is that right? Right now? I should be presenting.
Fast
You
and
guys, let's see. You guys can see yourselves okay?
You're gonna have to tell me pronounce your whole name correctly.
It's not the first time I've done
Snack.
yes.
Okay.
Spiridon.
Wait.
Spiridon?
Very done.
Spiridon?
Very
Or we're
done.
gonna pick command, so Spiro.
Spiro.
Which is easier.
Oh, I was telling you
Right.
it's Spiros, but it's Spiro.
Spiro.
Spiro. Well,
Spiro, okay.
so in Greek, if you're talking to a Greek person,
Yeah.
you just say Spiro.
Okay.
Right? Or Nico or whatever.
Oh.
If you're
Snack,
talking
why are we
to
not live?
another person, you put the S at the end.
Spiro.
So Spiro, welcome. Like
Well-
Spiros will tell us about.
Oh, okay.
Hang on a sec, guys. Hang on a sec.
We're holding on. We're waiting.
We got some. We're
None of us wore any colorful pieces.
busy. So we
All right,
just
we're live? Okay.
said we were wearing the same colors.
I know.
And then we're like, what if Spiro
I know.
shows up with the same colors? We're like
Color
triplets.
coordinate.
Hold on.
We're
Well,
triplets.
you were black too.
I'm wearing black.
It's like
We're all
it's like
like a little
a
mixture.
it's like a
We're all in
fading.
the same color.
It's like the it's like a
The gradient.
hue.
Yeah.
Yeah,
Darker, a
gradient.
little bit lighter, a little bit lighter.
Just
Like a
turn
tone.
black and then boom.
That's very sweet. I like that. We're all the same color. Okay, so Spiro, and then the last name.
Michalakis. So it's like
Yeah.
Michael,
Yeah.
little Michael. Akis comes from Crete, which is
Yeah.
the largest Greek island. And Akis is what you put at the end, I guess, of most Christian names.
Okay.
And it's little, when you put the Akis, it means like little Michael.
Okay.
Or little John.
Michael. Sure,
Yeah, Akis.
Michael.
Yeah.
Michael.
Obviously, I'm not that little, but you
So
know,
what is
We
it's
start-
always fun.
What is Spiro?
I always dreamt it meant something majestic, but Spiridon literally just means like a hand-woven basket by an old lady. And I was like,
Nice.
that'll do, you know, you can hold stuff in.
A vessel.
So, the
It's
best.
like a personally made vessel.
It's an intricate.
Yeah.
I would like to think so, yes.
Heritage. Perfect. All good things. Are we sound testing still?
Waiting for the control.
I think we're good.
You're from Greece.
Looks like we're live.
Where in
Yep.
Greece?
Okay, we are live.
Just outside of Athens. It's called
Just outside of
Sparta.
Athens. I've been to Athens.
Yeah.
And I've been to this little island called Ika. The little
Hydra.
Ika.
Ah, yes.
The names
Or Hydra.
are- yeah, Hydra,
Yeah,
like
Hydra.
water. It was the most beautiful thing I think I've ever seen. The blue waters.
You'd be surprised, there's another 2,000 such beautiful items.
Oh, there are.
You're like, oh my god. And then you put the
I
next
don't
one.
know. I don't know nothing.
Yeah.
Well, I'm gonna go to all of them. Are we ready?
We are live.
Okay. I gotta remember what I want to say. No, I'm just kidding. So thank you. This is Spiro Michalakalakalakis,
Nice.
and we met. I went to the Behind the Curve screening at the Los Angeles Film Festival. I saw you in the movie, and then I saw you in person standing outside, and I thought to myself, I would like to say hello to this person. And so I went up and I said hi, and asked you if you've ever met a flat earther before, and you said I was your first.
Yeah.
And then I invited you to meet with me and with others, and you surprised me so much because you took my email, and I didn't know, maybe that was like the end of it. And then you responded and you said, let's meet. And we've been having a really nice correspondence, set this up, and here you are, and it's super nice. And we really thank you for coming to talk to us.
Thank you for having me.
So, yeah.
Okay, Nathan.
Yeah, this is
You
Nick.
guys.
We're gonna
Sacha, honestly. And then on the panel we have Jibby. This is Poncho Pete's channel.
Hello.
Wait, where is Poncho?
Poncho is in England.
In
correct?
England.
Poncho?
Wow.
Poncho's in Grimsby.
Grimsby.
I've been in England, yes.
England. We have Josh there with the cat,
He's actually not too far from us.
and Nathan's on the panel as well. And we also have the guy that's running kid. His name is Snack, and he's the one that pushed all these magic buttons to make this work between him and I. We can do this live on YouTube. And
So I love this podcast. It's like a den of free speech, and it's really amazing. They go 24/7, and they've been going 24/7 for how long? Kenny?
this is day 713 in a row.
So people
24/7.
People get on here and they talk about flat Earth and they talk about their lives and they talk about anything, but they just like explore ideas around flat Earth and every way that it affects them. So people from all over the world get on here, and so I just thought it would be really great if we could talk like a little in person, and then also you can talk to them. And
Sure, yeah.
okay, fantastic.
Perfect.
So I want to introduce you, but I don't think I'm going to do it justice. So do you think you could talk about your
Sure.
job and
Yeah, I can say a
background?
little bit about myself. So I grew up in Greece. I guess we already mentioned that. I am the middle of three, all boys. And I found out that I loved math since I was a little kid because my grandma would just do these magic puzzles where she would ask me to come up with a number, keep it in my head. Then she would ask me to do multiplications, additions, subtractions. And then at the end, she would always figure out what number I had in my head. And I was like, this is magic. How is this possible? Right. So I remember the first time where I realized that math was magic was when I started writing down algebra before I took any algebra or anything, because there was, I had to figure out how was she doing that, right? I wanted to do magic, but also I wanted to know how to do it myself to others. Okay, like here. And then I wrote down p, which is the x in Greek for a variable. And then I started thinking, okay, what if I do retrace the steps she told me? And then I figured out what she was doing. The trick was that after all these things, she would then say, and now subtract the number that you had in your head at some point. And this was when the magic went away and it became always predictable, right? Because at that point, it didn't matter what you started with. It was always going to be the same answer. And I was like, 4, 5 years old or something like that. I was so frustrated I couldn't figure out that I started doing math. So and since then I fell in love with math. I mean, I remember taking piano lessons because I loved, piano, but at some point I stopped practicing because I fell in love with solving math puzzles, like harder and harder math puzzles. I would stay up until 3 in the morning. My parents thought I was watching TV. Tell me, go to sleep. And then there I was doing math. Right? Like, yeah. I wouldn't tell them. And then after that, I went to MIT for my undergraduate degree. I ended up studying computer science, but then I missed math, so I ended up double majoring in math and computer science. And then I went for a PhD at UC Davis, which is just north, right, near Sacramento. And it was an amazing experience because at MIT, it's one of the top places in the world, like Caltech, right? So everyone was so intense, it's like hardcore and all that stuff. And at Davis, everyone was so chill. And everyone was still having fun and they're doing research and they're doing their work. But there was amazing sushi. There was everyone was biking around and was healthy looking, right? So I love that place and I still visit as often as I can. And then after I got my PhD then, and I transferred from computer science and math into quantum physics. The reason why I actually went for quantum physics was Star Trek, of all things. The irony of all these is that I didn't even watch that much Star Trek, but just enough to know about the teleportation device that they had, beam me up, Scotty, and all that stuff. So the head of the math department at Davis told me hey, how about we work together on physics? And I said, but I don't know any physics. I hadn't taken any physics. He's like, don't worry, this is about quantum teleportation. Quantum teleportation, right? Both of these words are magical in most people's minds. And they were to me too, because I didn't know what they meant. I knew teleportation, it's magic. So I ended up studying this and then ended up becoming kind of an expert in quantum physics and quantum computing, which is this new cool stuff happening right now. And then I went to Los Alamos, which is where they developed the atomic bomb, I don't know, 50, 60 years ago or something like that, 70 years ago. And I didn't, of course, have any clearance to do anything like that. I didn't go to build any bombs.
Yeah.
I don't think they even do that anymore.
Did you see how they build the
I
bombs?
was
Did you get
outside
in
of the
person?
perimeter, apparently,
Okay.
because I'm still not a U.S. citizen.
Oh,
I have a
okay.
green card now, but, and the irony of it is that they had so many Russians who were citizens behind the fence, and I wasn't allowed to be, to go through. And we played volleyball together. They were great people. It was a lot of fun. But yeah, I ended up working on a very difficult problem. A millennium problem, it's called in mathematical physics.
I'm sorry, what was that?
Millennium problem,
Oh.
one of those like that. They set them up 18 years ago at the end of the last millennium. I was like, all right, we'll give humanity 1,000 years to solve these 13 problems. Some of them have $1 million prizes next to them. So then my advisor over there, because I had just finished with my PhD, and I was like, what am I going to do with my life? I guess I should go for a postdoc. This is what you do after you get your doctorate. If you want to go become a professor or something like that. And so my advisor said, hey, would you like to, work on something as a warm-up or something interesting? I'm like, I want to work on something interesting. It's like, here, try to solve this number 2 problem on the list of impossible problems. So it's like, he has a different sense of interesting than I do. So anyways, I ended up spending a year doing nothing but working on that problem. I ended up solving it. And it actually was recently announced, around the world. But it took 10 years for them to understand the solution, right? So I learned patience with the world. I learned to empathize with others that had spent all their life trying to understand and solve this problem, and made amazing progress. Many of them got Nobel Prizes, right, to make some progress on the solution. And still, when they saw this one, they're like, we don't know what to do.
But
right?
you took it home.
That's
so
right.
Nobel Prize winners tried and failed, and you succeeded.
I'm not gonna say anymore. So
when do you get your Nobel?
Yeah, we'll see.
Is it possible to summarize or to just give us the idea of what that problem was?
Yes. By now, I guess I had to do it for so many, different
sure,
magazines and whatnot. That the idea is this: that there's something magical that happens when you are transitioning from the quantum realm, right? Things as they happen at the microscopic scale, and when we come up to our level of reality, right? Where we're here and not here and there. Exactly, subatomic versus like classical physics, okay, where we're here. And we try to understand this transition, but one of the big open questions is, or was, I guess, how can we take the magic of the quantum realm and blow it up to our scale? One way of doing that, we're trying to do that with quantum computers, right? That's what they're supposed to do. Scale it up so we can manipulate at the quantum level reality without losing all the richness that it has at that level. And disappears when we go macro. So I was able to show how exactly this happens. What is the recipe for being able to create macroscopic quantum phenomena? And this can be used now for building what are called topological quantum computers, but a lot of other cool stuff too.
And it's amazing. And
the computers they use are the adiabatic computers?
So there is, yes. So some of them are adiabatic. And in fact, it's funny you brought up that word up, because that's a very deep word within mathematics and physics. Mm-hmm. And the main tool that the Nobel Prize winners had used was called adiabatic evolution, right? To try to adiabatic very slowly, without changing the energy of the systems, try to move around the system in some parameter space, and then explore that space, right? And I had to come up with my advisor with an even more general evolution, a topological evolution, one that transcended even adiabaticity. So, and that's what it was like so special.
Wow, okay.
So what is your what is your job now?
My job now is to stare at the wall and try to figure out how the universe comes to be. And also I do outreach to the public. So I have probably the best job in the world, I think. I have students that I work with, figure out what is called the theory of everything, which is, how do you bring together quantum physics with Einstein's relativity theory, but how do you actually go beyond both of them, right? How do you go underneath and unify them?
Okay, awesome. Now I'm going to ask you a flat Earth related question.
Yes.
So we're all flat Earthers. So you know that, it's no surprise. So, oh, okay. So I know that you, in the documentary, you spoke on flat Earth as a phenomenon, as a people, as a thing. And you've written at least one article talking about.
That's right. I was asked right after the documentary had a premiere in Canada, Hot Dogs.
Yeah.
What is it?
Yeah,
Dogs,
hot
that's a
dogs.
good name.
Sounds like hot dogs.
Yeah, I know. I was asked by one of the producers or McLean's in Canada. I didn't even know there was a big newspaper. It is a big newspaper up there. So yeah, I just wrote.
So I would love to hear about like how you formed your thoughts that you shared about flat Earth, and if you did any research or just what you experienced and what you think about us until this moment.
I see. Wow, that's it's a big question. I would say this, that the way I feel about your community is any community that is curious and is trying to find something beyond what is commonly accepted, right? So for example, my research has taken me to a place that goes beyond the craziest conspiracy theory you can come up with, okay? For example, like, our space and time fundamental concepts. Forget about whether the Earth is flat or not, right? Does space even exist?
We agree with you on
Okay,
that.
right? So that's one thing. The other one, and so it's actually at the cutting edge of physics right now, where we're saying like, you have to throw away even like Einstein's theory, okay, which is more general. That's what I want to clarify, that
general relativity.
It is more, exactly, the general relativity aspect. It is a generalization of the concept of flatness, okay? Because if you think about this room, this looks very flat, right? But I mean, anywhere you go, even if it was a sphere and you're locally looking at it, it's going to look flat. And you don't know, actually, very often you have to zoom out all the way potentially, or find some other way to look if there is a curvature or not, right? You have to like look at larger distances. Right. And that's the beauty of like Einstein's theory, that it unifies new possibilities, right? That say, yes, this could all be flat. Because if you look locally, yes, if you have a bunch of flat things, you put them together, you expect it will continue to be flat. But it says something else, that it is possible. There is no reason, right, why even though little pieces of the puzzle like look flat individually, that you have to put them at the same angle. Sure. You could potentially, like, as you're moving around, you can rotate them, you can twist them a little bit, you can create crazy, like it could be a donut for all we know, right? And you don't know, again, unless you go a little bit more global, or you go, further out. And that's, I think, the beauty of the idea of relativity, that from my point of view, like goes not just beyond a flat Earth idea that, the Earth is flat, it could be, okay? But it goes beyond even the idea, there's a deeper idea within quantum physics that goes even beyond Einstein's theory of general relativity, right? And relativity means what? It means that somehow we are given the freedom to choose how these pieces are patched together, right? One very special case is when they're all put together in a globally flat way, okay? That they're all like, we are all seeing uniformly the same thing, whether we're here or we move around. Mm-hmm. A more general case is that, there's a little tilt between them. You can move them around and all stuff, right? Yeah. And as this is happening, you think that you should all agree on your observations, right? Mm-hmm. You're seeing the same thing I'm seeing, but because you're rotated, your coordinate system, right, has changed. And unless you keep that in mind, you will start saying like, no, but this makes no sense. What is this? Where did this come from? We're just measuring the same thing. Why are you getting twice as long in time or in space or something like that?
So is that sort of like your feeling of like why it's not flat? Is that? Oh,
it's not even that. I mean, I again, as I said, I'm so much crazier even than Einstein, right? That it is such a beautiful. It's not a theory. It is a framework, right? And now you will think at the end of this conversation that I'm the crazy one. Okay. So
that's our goal. We have that goal. You're more crazy than we are.
You'll see.
So I set a high ceiling.
And but this is like what I love about physics, the way it has been done so far, right? That every 100 years or so, the previous main ideas and theories are now thought to be just like, oh, come on, you weren't thinking broadly enough, right?
So I have a sort of a question just about flat earthers. Now, I can't quite tell because you're being so nice. So I can't quite tell if you think flat earth theory is flat out wrong or if you just
yes,
don't
I
know,
will be okay.
or-
So let me clarify my position. I do think that the theory is wrong,
yeah.
right? The reasons why I think that are not just scientific.
Yeah.
And this is maybe where we're trying to get to, right? And this is also what I described in the documentary. That I want to ask you a question.
Yeah, you
okay,
can
here.
ask us anything you want.
Do you trust astronauts? And if not, why? Right? And if not astronauts, do you trust something in the government? What about scientists? What about Carl Sagan? And at which point would you be willing to trust other people outside of the flat Earth community? Right?
Sure.
And what would it take? And that's like,
Can we,
yeah, go ahead.
Yeah, we can answer that. Absolutely. Dude,
can-
you can go first. Yeah.
personally, I don't trust astronauts, and I also don't trust our government. And as far as what it would take, or what I do trust, is my observations and what I observe in reality, and the shared reality that we all experience together. I don't trust NASA because there's been countless time after time, hundreds of pieces of evidence that show that they manipulate stuff using CGI. They
start to look at the different contradictions that like some of the astronauts like talk about, like for example Michael Collins, when he was asked immediately after in the press conference, they asked him if he saw any stars, and he kind of looked confused and he was like, I don't remember seeing anything at all. So even though he was supposedly in the orbiter while Neil and Buzz were on the moon, he was circling. So he was on the dark side of the moon, supposedly, right? So, I mean, you can imagine what the view would be like, but he said he didn't see it. Then in his book that he wrote years later, he said it was the most magical, said it was the most magical, wonderful thing that he's ever seen, and he could see the stars everywhere.
Yeah.
So like things like that, when the actual astronauts themselves are contradicting what they did say. So then you start thinking, well, what do the other astronauts say about whether or not you can see stars from space? And it's completely opposite. Like some of them say it's you can see nebulas and you can see like all the different points and they don't twinkle because you're not looking through the atmosphere. And the others say it's like a just velvet sheen of the blackest black you could possibly imagine. So like, when you have a memory and you really start to look at the contradictions, the things that are literally opposite to each other, the distrust starts. It's like, well, then, why did this person see this and this other person see this? So then you start to do a little bit more. I mean, from what I found, like every aspect of NASA and the astronauts contains just unbelievable contradictions.
I certainly didn't want to stop believing. I loved the idea of space travel, and when I went to grade school, we had one of the Mars rover or some kind of apparatus, like on the wall. Supposedly it was the real one, and I was like, is it safe to touch it? Like, that's my school, but I didn't. You're in question, but it was a few years ago when I started looking into this, and it was like I became like a detective. Like I went on my own adventures and I went to science centers. I went to science centers and I asked them questions and I compared counter arguments, you know, like an 8-hour story of my journey because I did it for months. But basically it was like a realization that it would be possible to lie. That it's not just like, oh, I don't trust the government. It's just like, could they be lying? Is there a way for me to verify it? And I realized it was diabolical, but it was possible. Just in the same way that propaganda exists. And, you know, they in North Korea, they put on shows, they make them believe things. And we know they believe these propaganda stories with passion. And to me, it was kind of like, could that happen in America? Or could that happen in the Western world? Or could that happen on a grander scale? And it wasn't that I wanted it to happen. And it wasn't that I was like, I'm so suspicious. It was just the evidence piled up. And I was like, I think it is happening. I think, because I know about theater, I know about stagecraft, I know about film, and like how you movie magic. So I started to look at the footage of space travel, and I saw stagecraft. I saw green screens and harnesses, and it was just shocking. And I had to re-look at it. Am I really seeing that? Like, so I went through a process of, I don't know. I gotta say, I didn't have a motive to see it. I just started to see it and it accumulated, and then yeah, I did decide that I don't think it's real. I don't think they're really going to space.
One of the and something I wrote, I think, and I talked about also in the documentary, but I wrote in that article, is for me it's empathy, right? Which is very hard to have empathy with others for the same reason that others, you know, find it very hard to have empathy with you when you're diametrically opposed in many ways. But to find humanity in each other, right? And it is very difficult to do that. But one of the things that I consider important, and I have a little anecdote from a couple of summers ago. I think 2 summers ago, I was back in Greece. I try to visit my parents every summer. And one of my good friends, she is this Olympic volleyball player. I love playing volleyball, but like she's at a different level and everything. And you know, after we played some volleyball and we go into the sea, and it was just a hot day. It felt great to be in the cool water. And she asked me, she's like, Spiros, do you think that the cure for cancer already exists? That big pharma is like, you know, right? How many of you believe that the cure for cancer already exists?
I think there's a lot of ways to prevent it that we
And
have not
I
enough
do
freedom to talk
believe-
about it.
I know people that have cured themselves from cancer.
Okay.
Yeah.
So
Yeah,
Doing
it's
strong
strong
theory.
possibility.
Yeah.
Sure.
Okay.
I think there's multiple cures for cancer.
So the way I feel about this is as follows, and this is also how I responded to her. Right? I said, there is definitely a possibility, but as someone who is part of a community of good people, right, who spend day and night either trying to figure out how the universe works or to cure cancer, can you imagine how upsetting it is for someone to say like, oh no, this is easy, you guys already figured it out, you're just keeping it from the rest of the world, right?
Yeah.
That's what I told her,
That's-
I'm gonna be honest, right? It's the same way that I felt, I'm just gonna put it out there in public,
Yeah,
hopefully
please.
my advisor won't see that from my postdoc, but
You won't see
he
this.
thought, okay, he thought that it shouldn't be so hard for me to solve that problem. And I was like, you know, what's taking you so long? Solve this millennium problem, right?
The one that's never been
I know,
solved.
exactly.
The one that
With all the
Nobel
Nobel
Prize
Prizes.
winners.
But so
And-
why didn't he do it?
Hey, I'm not gonna say anything. So it just, you know,
Well,
took
I-
the wind out of me, right?
Yeah.
Because it trivialized all the work I was doing.
I think that I'm kind of picking up on what you're saying, and there's something like I really wanted to be able to say to you and to I guess to scientists in general. But I mean, I do not feel in opposition to science, and I I mean, sometimes flat earthers will say scientism, and they're trying to talk about a dogma that's enforced in the name of science. But honestly, we want to keep science true and real, and we want to use the scientific method to verify, and we value the idea of checks and balances. Just the idea of like, if isn't science different than belief in the sense that we can explore counter evidence at any stage in the game.
Yes. I think that's, you have put it very beautifully there, but I will turn it around against every single one of you right now, right? Yeah. And this is my strongest argument. Yeah. Right? The best argument, and I think maybe you asked me or someone asked me after the documentary, they said like, how do you know that the earth is not flat? I'm going to be honest, right? Like, you know, the first argument is that I just have faith in people. I try to see like right away, you know, the best in them unless I see otherwise. And you said, you know, the same thing often, right? You didn't want to believe that they were lying, but so I start like that also. And since I have so many friends now at JPL, but in other places around the world, right? And not just talking about space, biochemists, like, you know, quantum physicists, people that I don't even know very much about space, right? You know, I wasn't the kid that was like looking up in the stars, I want to be an astrophysicist. That wasn't me. I just wanted to do my math, remember? But in science is not dogmatic in a very strange way. Yeah. The very first step is dogmatic because it says, and you'd be surprised by me saying that, observe the universe. Okay, go out there and observe. That actually is the only dogmatic step of science, which sounds counterintuitive, right? Like, what do you mean? You should, like, you know, if there's evidence, right? This is how you should build your theory, the evidence. Imagine that the ability we have of observing filters away what is really going on, okay? Then the very first step of science is faulty. Why? Because it's not going to figure out the true theory of how things work. It will figure out the theory of your observable universe, the one that you can actually observe with whatever powers you have at whatever point in space and time you're in, right? And that's why we become better and better, and we can do more stuff, because we keep expanding what we are able to see or how we are able to see the world. So that's one thing. The next step in science, which is the more interesting one, is that then you come up with a hypothesis, right? You're like, all right, you know, does this fit, right? The evidence, but you have a theory, you have a model, okay? What do? You feed in the thing, and then the model is supposed to make predictions. And if it makes predictions that are like kind of strange, you're like, all right, this is interesting, okay? It doesn't just verify itself. Maybe it predicts that like this also should happen, okay? For example, at the end of the documentary, your Corps of Engineers, right, is doing the laser experiment twice, okay? There's the gyro experiment, there's that. And so you have a theory, the Earth is flat. So, and this is actually beautiful because your own Corps of Engineers said, okay, so if the Earth is flat, we should see zero inclination. If the Earth is flat, we should hold it like here, and it'll be like perfectly straight. You know, you'll be able to see it, and you'll see the reflection and stuff. I was like, this is amazing. This is really scientific. This is ingenious, right? I would, you know, I haven't done this experiment, right? So I don't know, as much as the person who did the experiments, what the answer would be. I was like, kind of waiting too, you know, hey, what's happening?
There's a lot of flat earthers going out and doing practical. Yeah. For me, it reminds me of an outsider science.
Yes, a citizen science too. Yeah, I love that.
You know, I think of like outsider art, you know, rising to the you don't have to go to art school to be a genius, and so I appreciate that you don't have to have a formal degree in science to be able to observe the world and do experiments.
And you know, the amazing thing is that in the beginning, there were no scientists. There wasn't like, humanity wasn't born with like, oh yeah, there's a bunch of people that are going to be born scientists, and but like there was, even until like Newton, the word science didn't even exist. What does it even mean, right? And Popper and others who came up with a philosophy of science, right? The things I was describing.
They all started out unaccredited and
yes, there is no such thing as Einstein. Right?
So can I ask you, you mentioned the test that they did in the documentary.
Yes.
Are those the only experiments that you've seen?
I actually, honestly, yeah, you know,
So
this
I
was
don't-
also from your side. I was like, this is ingenious, and what I wanted to kind of say, just to close this like circle of
Yeah.
science, is that the last part of science is its true saving grace, the thing that allows it to go beyond its own dogma of what I observe is all the data I stuck with, right? Which is that the theory part allows you, because it is abstract and mathematical, to go beyond physical reality, right? It goes beyond even whether the Earth is flat or the Earth is a globe or the Earth is a donut or the Earth doesn't even exist, right? It allows you to go to a space beyond, an ambient space of possibilities, and then you can test for new evidence and predictions and try to look for evidence like you guys have been doing, right? Like, oh, once you start seeing something, like start unraveling this. And that's, I think, like interesting, right?
If it's beyond outside of what we can observe, how can you actually verify that it's true and that it's real?
Okay, so very good question, right? The theory, right, will give you guidance of where to look.
Yeah.
It is before the probability, and it comes down to chance, right? Very often. That's why we say, oh, we had the discovery, it just came out of nowhere. If you don't know where to look, there are so many possibilities that you will not find, or you may end up looking at the same place again and again. And in fact, this is a very deep question. This is a very deep question you ask, right? Because all of reality, I believe, including all of the laws of physics and all the structure that we see, is emergent, which means that there is a mechanism that ends up feeding us what the mechanism thinks we want to see. Not just even like a matrix or simulation, but more like certain things become much more likely than others, even though if you look underneath, right, say you're looking at biological systems, but then you start looking at the chemistry of them, you go to the level below, all the patterns and laws that existed up there start to dissolve away. They're gone, right? They don't exist yet. Just like we are not here. We're not talking. There is no such thing, right? You know, there is my arm doesn't exist. This chair doesn't exist. If you zoom in, there is no such thing as chair, right? There's a bunch of like molecules. You zoom in further, there's atoms. And then you zoom in further and further, you change your point of view, they all go away. We never even touch anything.
My
right?
experience is chair.
Exactly. And this is the macro experience, right?
So
this
it should come.
the shared experience.
Should that not come full circle after that third step back to the first step?
Exactly.
And
Exactly.
to-
So
You want to see something?
Chippy wants to jump in.
Hey, there's a
Yes.
guy in the panel. that wants to-
yes, please.
Chippy, you there? Yes, unmute. There you go.
I'm here. Can you guys hear me, see me, any of that?
Okay, I can't hear.
Oh,
Okay. All right. I just wanted to welcome you, Spiros. Thank you for joining us.
thank you.
I hear you're a consultant on the Marvel Studios movies.
Yes.
All right, I have a question then. How do we reverse Thanos' snap on a flat Earth?
I'm not even joking. I think I wouldn't make it out alive if I told you the answer. There's a lot of people want to know.
A lot of contrast.
I have an idea, but yeah, a lot of people want to know. But it goes down to some of the things I'm describing right now, right? Down at the quantum realm, space and time as notions, and I had them say that, right? You know, in the movie, Michael Douglas says that they lose their meaning, then you can do a lot of things, right? Not just even within the Einsteinian theory of like moving through space by moving through time and all that stuff, but just, you know, it is so beautiful actually when you start seeing what is really going on. It's so mind-boggling.
So what
It
is
comes
the,
down to that.
What is the physical manifestation of what you do? Or
Staring at a wall.
that's what I'm asking you. I
Yeah.
know it exists on the wall. I know it exists on the paper, but
Yeah.
how does it come full circle back into
It's a
observation?
Oh, yeah,
different-
that's
it's
a-
different kind of-
Yes, but no, you have a very good point, right? So how do you check that you're not just going out to La La Land, right? And in fact, you know, how can you do that if your reason for being as a scientist is to really do go out to La La Land, right? Here is how it's done. Okay, it's exactly the same way that 100 years ago, people like Einstein, and people like Schrödinger and Heisenberg, right? You know, individually we're fighting each other because one, Einstein didn't believe in quantum physics, but like people didn't believe in his theory back then either because he was like too far out. But all of a sudden, from these theories, now we have GPS, okay? You have the ability to like geolocate yourself that we didn't have 10, 15 years ago. I mean, I grew up and you needed an actual map, paper map. It was a pain in the ass, right? Now it's just your phone can do that. Forget even about the GPS. Maybe you don't believe, right? You know, this is actually all happening in a satellite. It's fine. Think about like the quantum physics that goes into the microprocessors, right? And the resonators and all the stuff that exist in your cell phone so that you can do magic. Because back then, they didn't even know that electricity existed. They didn't know. They were like, you get zapped, lightning hits you or whatever, but they didn't know there were electrons or there's like that light travels, you know, with the speed of light, or there's electromagnetic waves, and different ones allow us to see differently or hear differently or communicate with invisible waves. So my point is that the theories that I'm describing right now, that I'm exploring, are the ones that open up like an origami and allow you to start like asking new questions. That you're like, is it possible to time travel? Is it possible to teleport? If you can manipulate, if you understand what space is, and it's not the foundational canvas upon which you're stuck, right? But if you understand what it is made of, then you can reverse engineer it. Just like you could reverse engineer electromagnetic waves and radio waves and all that stuff, and you can do magic.
Space as in outer space or space?
No, as in space as a concept. Well,
Space
no.
has a
Like as an object, like Emmanuel, like in critical cubism, right?
I wanna see if so.
Yeah.
What is space made of?
What is it, man?
So we could probably spend
Yeah.
20 hours talking
I
about
wanted to finish
the-
like that circle,
Yeah.
but come back to what you were asking earlier, right? Which was the laser experiment that I saw and the
Yeah.
gyro, right? So this is where I wanted to bring it back to you, and I want to hear what you have to say. So the Corps of Engineers, the FE Corps, right? I love that name. They say, you know, if we see 0 degrees, it is flat. According to the ballers.
You got it. You're
It's
down.
so cool, you know.
You got
Thank
the
you.
lingo.
You're very kind. You know. According to the ballers, there should be like a 15%, like, you know, they'll see 15 or something like that, right? And it was a $20,000 piece of equipment. I was like, this is insane. And then they turn it on, like, yep, 15. Like, shit. Okay, well, that's interesting. So my question is, first this happens, then the kid does like this awesome experiment with the laser, which is hard to focus to. Sees exactly the same thing, like, well, yeah, if the Earth is curved, then you have to go higher up, you know, so I can see you back. So just wait for a second, right? And this is where you start feeling inside, damn it, I want to say something to this guy. But think of it from a very simple point of view. Okay, you did the experiment, you had the theory, you were wrong. What now? There's 2 choices, right? Either to say, right, well, okay, that's it. You know, there's no other way around it, or to dig deeper, right? To go even deeper and be like, okay, but wait, maybe I need to change the theory a bit, right? You know, maybe there's something I'm missing, and so on and so forth. So, how deep are you willing to go? Okay, and given that about 400 or 500, I don't know, when was Copernicus and Galileo? About 500 years ago or something, right? Before the heliocentric system, right? There was this amazingly complex but beautiful way of describing how all the stars and planets moved around each other with epicycles and all that stuff, okay? And then what happened? One day somebody said, what if the sun is in the middle, and then all these things are rotating, a massive body, we're rotating smaller around it. And all of a sudden it became so simple, right? It simplified exceptionally. So it is possible that you create this very intricate and complex model that ends up feeding, like every time you have to explain something, you have to add it as well, okay? Or you just have a single, like, you know, model that says the Earth is round, and this is why you saw 15%, this is why they had to do that, this is why there's all these pictures of the thing, of like people traveling, all these trillions relative to like any evidence you will ever provide, right? I guarantee it'd be like trillion to 1 that the Earth is a globe. So how will you actually say that, all right, this is where I stop?
It's a trillion to one that it's flat.
So it's,
That'll be amazing. Like, I'll be amazed.
Doesn't that all self-apply what you just said? Doesn't that all self-apply to you in terms of like what it takes to check out a paradigm that you're unfamiliar with? And when the evidence in your globe model were to break down, that you would naturally want to check it out. So I applaud you in that.
Yeah, of course.
It's funny, when I was a kid, I celebrated Copernicus' birthday. It was we celebrated, a strange kid. I wasn't my age.
Okay.
We celebrated Darwin's birthday and Copernicus' birthday.
Yes.
And on Copernicus' birthday, we ate Milky Ways. And we talked about how we were not the center of the universe. And we called it Anti-Dogma Week. We celebrated the idea. This is what I was raised on. We celebrated the idea of observation and science and overcoming religious dogma, and the story of Copernicus, against all odds, giving people a new way of looking at things.
Hey, anybody on the panel got any questions?
I want to set up Nathan. So
Okay.
Yeah, I also wanted to ask, Spiros, how long do you have with us this evening? We're really enjoying this. I just wanted to keep going.
Yeah. So,
Okay, yeah. I mean, I can be here
We
for
can
another
take a
like.
break,
No, I'm happy to stay here until we,
Yeah,
I want to take time to Nathan. I'm gonna have Jai talk, but I want to make sure that Nathan gets a chance to present his experiments,
go ahead, Jay.
and then we're gonna give it all to
All right,
him.
Nathan.
That's
Nathan,
awesome. Can we
take it
go to
over.
that next?
So just
And just right now, if we were to get a bottle of wine, would that make Spiros stay another hour?
We got some beer.
We can afford brown liquor too.
He's great.
This is great.
One right. The trick question.
I'm Italian. So let's do it.
Yeah. No, sure. Bring
I don't think we have wine, but we have beer. Do we have wine?
I don't know.
Wow.
Do we have wine? I don't think we do.
It's fine. It's no, I'm good.
Yeah.
I'm happy
Wants
with
to go get one?
So you have a little bit of time to spare?
Yeah.
Okay.
Jai.
Jai.
Just, in relation to a couple other things you said, we are in agreement in that we are very, very interested in the nature of reality. Like we want to know the truth, whatever that is, both on the quantum level, also on the physical level. And I think like a distinction needs to be made in terms of like the term flat earthers is kind of a loaded term. And when you say that to somebody or when you hear it, like there's all these ideas that are in there. So I think the one thing that flat earthers agree upon is that we're globe deniers, meaning the model that we've been given, the model that we were taught, that we're on a giant spinning ball, and this ball is hurtling around the sun at breakneck speeds. The entire idea of the heliocentric model, we are away from that. We consider the globe model dead.
Can I ask you why you describe it at breakneck speeds? Does this mean something to you? That is supposed to mean that like, oh, why isn't it that we're like not flying out or something like that? Or why does it sound like?
Meaning, the speed is 66,000 miles an hour, and then you have the entire solar system.
And it's all
going around
that's right.
like several million miles an hour, and
that is actually.
So
I'm gonna say this is true, even though it may think like it's not true. But from the point of view of relativity, but also very simply, when you're in a train, it's going 100 miles an hour, right? You're standing still. You're not thinking like, oh my God, I'm going to die because I'm going 100 miles an hour. Somebody from the outside who's looking at you is like, holy crap, they're moving really fast, right? But you yourself, you're like, no, just
a train is an enclosed system. So is it your view that?
Oh yeah, exactly. I mean, that's right. Like that's of course that's the idea of wind, right? That when you get winds, it's not that they're blowing towards you; they're just blowing up, and then you're like, oh shit.
There's one thing I just want to throw in there is that on a ball, the equator has to spin about 1,000 miles per hour to make one rotation per day at 24.
That's about something like that.
A little bit more.
2024.
1,024. We know. We're like.
2024. It's a power of 2.
We're nutty. We learn all this stuff.
Yeah,
so the equator has to spin at a little more than 24,000 miles an hour. 1,000 miles an hour.
Yeah.
But as you go up to either or down, or well, relatively to either pole, you had a more tapered
That's right.
journey.
So, yes.
So you have
Your angular velocity is smaller. Or
so you're literally going slower. So like if you're in India and you travel to England, the ground beneath your feet and the atmosphere slows down by 400 miles per hour. And so that's like I know we don't feel constant speed, but we feel change in speed. So it's,
Yes.
But there's compound angular momentum as well. So you're spinning 1,024 miles per hour. And you're spinning 66,000 miles per hour around the sun.
Yeah.
The sun is shooting 660,000 miles per hour through the galaxy, and the galaxy is shooting 6 million miles.
Agreed.
So there's four different
Of course.
speeds. And
There's
so
even more that we don't even know.
Yeah.
So you should be able to view some sort of evidence of that spin, which is something that we don't see.
Of what spin?
Parallax of the stars.
So if you wrote
Parallax.
a train that was going 100 miles per hour, and then you rotated it at like 10 miles per hour, and then you shot it at like 6,000 miles per hour, that'd be a better example or more equal comparison of what they claim.
Sure, we can feel what we can feel. Yes, and this is actually Einstein's brilliant idea that you cannot.
How about just perceiving in some way the gravitational pull that must be going from the sun to the earth while its own weight and the moon are being hurled around? I mean, isn't that a tremendous amount of force necessary to hold it back?
Oh, that's why the Earth is like a massive mass, right? And that's the kind of force that you need between them, so you can keep them together. But I guess what I want to say is something else. Imagine you have like just these old LP or LP whatever players with the phonograms, right? And you put a ball towards the center and then a ball like towards the end, right? It's not going to be that one of them is like, oh my God, I'm dying. Like, woo, I'm going like, I'm so far away. Look at me. Like, and the other one, they're both going to be rotating at the same amount locally. You won't be able to tell any difference.
I mean, if I'm on a merry-go-round and I go to the edge, I can like fly off like that.
But the
If I
reason
stand
why,
in the middle,
that's
I can
right.
stand.
Yes, and the reason is because acceleration. That's the second order effect. The first, that's gravity, right? Gravity is a name for something that is called like a second order effect. Like the first order effect is locally. You don't see every one of us right now, even though we're moving at crazy speeds relative to each other. We're still in this room, right? But if
Spiros, what is your favorable equation for gravity to calculate gravity? I know we have like Newton's law of gravitation, but
Einstein, Newtonian gravity.
You mean the one beyond that? Like because
the one that basically that NASA and SpaceX have been using that seems to work to calculate fuel and trajectory around these gravitational objects.
Advanced versions, solvable, but advanced versions of Einstein's equation that go beyond Newton's G m1 m2 over r squared. And that's the beauty of it too, that you can even see light, which has no mass, like gravitate around massive bodies, and you get to see three images.
So gravity is affecting light.
Yes, exactly. So gravity.
So then light contains mass.
No. That's the beauty of the. You probably know this, but that's the beauty of the theory of gravity. That it's not even about the force. It is an illusion of a force. It is something much deeper. It is actually the curvature of space-time itself, not space, not like the Earth or something like that, of space-time itself, as if like as you move from point.
Is that the theory of everything, quantum gravitation?
Oh no, this is just a wish. This is just a theory of general relativity. If you put quantum gravity in it, that gets more interesting. That's what I work on. But,
so this is how they reverse Thanos' snap. I get it now.
It all comes back.
Gravity can do it all.
Yeah, see, I know that they want to.
Can we break down Newton's equation real quick?
Yeah.
Would you like to do that?
Yes, Spiros. You keep mentioning gravity, man.
So
you seem like a really, really smart guy. You seem like a really fun guy, actually. It'd be fun to chill with you and like grab a beer one day, man.
Cool.
But as far as this whole gravity thing, I think I'll use Poncho's example with the barrel. If I had a barrel across the room from you, right? Could you tell me the mass of the barrel without having to get up from your chair?
How would I do that? How would I measure the force between us? Is that what you're asking?
No, I'm just asking the mass of the barrel. Like, tell me.
Knowing the mass just from
Yeah, just tell me like how heavy the barrel is, the mass of the barrel, like what's inside it.
If you can, so this is what you can do, and this is what science does. I think I know where you're going with that, right? Imagine that you can actually go to the barrel and like weigh it, right? Because the mass comes out usually from the weight, but you need to have a like this constant G and all that stuff. So usually you can measure mass, but through a proxy, or the weight, the force, right? And then if you can do that, then you can walk away and be like, forget I went there. Let me look at my calculation, or let me actually connect through Wi-Fi, a scale that I put the barrel on, and then I'll be able to see without even going there. Now from that, you can say, okay, it works with every single object I've ever done this with, right? And I can successfully measure their mass because I take it, I double it in mass, and then the weight doubles and all stuff. Then you can extrapolate, right? It makes sense, and say, okay, what if this is a massive object out there? How much would it weigh, and what would the force be? And it turned out that Newton was able to figure out a very beautiful equation, which was wrong. Okay, it was very right for very macroscopic, long distances, massive objects. But then Einstein was like, what if an object with no mass, like light, okay, where the mass is actually energy, two are like interconverted. What if such an object still gravitates, can still be bent around or feels force? It was insane. We were like, there's no way. Okay? What if this happens? What if gravity is not some force between objects with mass, but it is a thing on top of which all massive objects live on, right? Space-time, okay? And then the relationship between each other and how they move around each other through space-time depends on like the curvature of that thing. Like if you have, for example, a sheet of paper and then it is a little bit curved, you put the little balls, if it is flat, they're not going to do anything. They're just going to stay. Right?
Can I just stop you real quick right there? Because first off, you said science's favorite word, imagine. Just keep that in mind. But on top of that, let's just stick with the basics as far as tell me what's inside the barrel, bro. Because there's no way you know. Like, you don't know whether it's full of a liquid, whether it could be full of cement, it could be full of dirt, it could be full of styrofoam.
Yeah,
you have
right.
no idea.
Yeah.
Because even you said earlier that you would have to go to it, weigh it, and then you said you have to forget that you even went there. That's just, I don't understand.
Why are you asking whether what it is made of? I mean, if you can observe.
Well, I'm just asking like the mass of something, because like when you, like if you are looking at a celestial body,
yes.
And it's a good distance away from you,
yeah.
There's no way you know what's in the center of it. Like
there's no way to determine the mass.
There is like at least, and again, I described like how scientists think about this stuff, right? Because
yes, they imagine it.
Yeah, exactly. You have to imagine it, but you have to have faith that so far everything you have done, because you didn't believe you could, measure the mass of something nearby you, but then you did it. Then you traveled a little further, and then you measured the mass of something else, and then you extrapolate. I agree, right? We don't know what is out there, but if it works every single time for every other object, and your method works, and you create a theory that's...
How does it work?
What was that?
How does it
How
work?
does it work? By looking at something, Spiros. How does it work? I look at the moon, I've got the diameter, the circumference, but I can't see around the back of it. I don't know what's in it, but I'm going to measure the mass of it.
Okay. So I see what you're saying. So how do you know, how do you figure out without actually weighing it on something, right? So yes, this is where the theory comes in that says there's an equation for smaller things that are close to us, okay? This is Newton's equation, and we know how that works. So
they canceled out
well,
those.
But that's smaller things that you're able to touch, feel, experience, though.
correct. You're absolutely right. But then you could measure something with very small mass. The equation works, right? And then you get bigger mass. Then you get a whole house, or you get
bigger visual mass.
And you get no, not just visual mass. Like you measure it. Like you have a scale where you measure like how much weight you put on, right? And then if you eat, you're gonna end up like weighing more and more and more, right? It's not an illusion. And then you're like, okay, I trust this. Maybe it's gonna fail after some time, but I'm gonna create a theory based on this. You have nothing
right,
better.
But they have hollow moon theory. There's lots of theories about the moon, whether it's hollow or not.
Right? When it's looking down on us, but I guess
I can agree with this for measuring a sack of groceries. I can't really say that measuring a celestial body would be as accurate.
But what if so then you have a problem with additivity of mass. That if you like put a bunch of like sacks of groceries and fill like something as big as the moon with them, that you wouldn't know how much it weighs.
Yeah, because you're not looking inside it. You don't know what's in the moon. You don't know what's in the sun.
Sure. I agree that like you don't know if it's a sack of potatoes or rice inside. But if you had some way of figuring out on average what the composition, what the elements.
But we don't with those celestial bodies.
We do. That's the beauty of it, right? That's how we can tell like through spectroscopic.
We don't.
Oh no. I mean, like what I'm trying to say is that there are scientific methods that allow you to figure out the composition, and that's where quantum physics comes in. We had to go beyond Einstein to figure that out. So you're right. Up to that point, we just had to make up stuff, right? But then when you can actually shoot like electromagnetic waves, and then you end up getting back different spectra, right? You're exciting the atoms inside of these stars or inside of these planets and whatnot, and you end up getting back information that says, well, we got like this little like spectrographic information that says only certain excitations came back to us. Only certain like wavelengths of light came back from that place.
I wanna.
And by the way, just to quickly finish, there's a unique signature because of quantum physics, like hydrogen, iron, and so on and so forth. Each one of them has its own code. That when you get information back, you're like, oh shit, this is mostly made of iron. Or like there's water or something crazy like that, right? Because hydrogen and oxygen would have this specific signature, and it's not continuous even. It's like you clearly see like peak, then nothing, then peak again. Very cool, right?
So the answer is you can weigh a barrel checking what color it is.
Exactly.
If it's barrel colored, it must be a barrel. It's weigh a certain amount. I don't want to die. I don't want to like spend too much time on it.
I want you to be able to do this with them for like as long as you will. Okay. But I wanted
Nathan, cool.
Doing physical experiments out on the water.
Yeah, Nathan.
I want you to be able to see, kind of as a scientist, as a Caltech representative, I would love for you to be able to see some of his experiments and I showed you. Yeah.
So I didn't see the documentary, but I heard that those experiments in the documentary didn't go so well. So it's just like
they actually went great.
Oh, yeah. I mean, it went great for you because
I'm saying like not for me, right? This is very important. Yeah. I think we have to agree on this one that there was no demon like hiding behind the machines or any of that stuff. Those were people that went there, right, and said like, all right, we're gonna do this.
Right.
And hopefully we're gonna see zero, and we're not gonna need to do anything else. So that was my original question to you. Why were you willing to make the experiments in the first place if you were okay, if you were not okay with what ended up happening?
I mean,
that's deep, right?
So I wanted to
that's deep.
To bring it back to the experiments, and just like with your millennium equation, I'm sure it took you more than one time to solve it, right? How many times did you fail solving that mathematical equation? How many times did you have to erase the board and start over?
Yeah,
a lot, I would assume. Right?
But the problem was different from the point of view that once I solved it, I knew I solved it.
Right. So
like that was the difference. It wasn't like that I solved it, but then I was like, shit, no, this cannot be the answer, right? I don't want this to be the answer.
Right.
That's more important. I don't want this to be the answer. And then I went back and said, oh shit, like where do I take it apart again, right?
So my point is that you didn't solve it your first go, and you kept trying.
Oh, yeah.
Because in
That's all of
science,
science.
in science, you got to repeat your experiment multiple times, and you got to observe it.
Yes.
Repeat it,
Yes.
keep going, and no matter what the result you get, you keep going because you got to collect a wide variety of data.
Yes.
So Jaren's
okay, sorry to interrupt you because you're bringing up a very important point. How do you know that you have discovery in science, right? Because how do you know that you can stop? And this is amazing because Newton, when he came up with his equation, right, he's like, yeah, 100% of the time it's right. But it wasn't 100% of the time. It was 99.5% of the time because he couldn't see the 0.5% because, again, either the masses were too small or whatever. The quantum effects wouldn't kick in. And every time, science, and the most stringent of all sciences is physics. I don't take mathematics like as a science because you have to be 100% like that, right? But in physics, do you know what the burden of proof is? It's much more stringent than biology and chemistry and other ones, right? It is not 2 standard deviations away from the expectation. It is 5 standard deviations. It has to be a 1 in 3.5 million chance that you were wrong. When the gravitational wave detection at Caltech happened, when the Higgs boson, like, any of that stuff, right? They had the data for so long, but they had to cross-reference it in every possible way they could imagine, make sure that the errors would go away, and whatever they saw was not just a blink in the signal that meant nothing. So if you do something 1,000,000 times and you get the same answer, 15 degrees, and you always have to raise the same amount, like, the thing for the laser thing, then you're like, yeah, that's pretty good. Even though there may be quantum fluctuations, or, and I'm not even joking about this, right? You could jump from a global Earth to a parallel universe where it's flat for a second or even for like a few years and then go back to it. But as humans, you have to have some certainty, some truncation. At some point you have to say like, all right, that's enough.
So,
right?
So repeatability is...
And it's also important for your side as well, because if like you do an experiment and you're like, holy crap, it's flat, I got 0, right? I guarantee all of you right now, you would be celebrating and you wouldn't be like, all right, let's go back and do this 1,000,000 more times.
I mean,
right? Well, okay, so what I've been doing is, I have, like I said, I haven't seen it, but
yes.
Back in April, me and a group of friends of mine, there was a team of scientists that issued a challenge to prove curvature on a large body of water at Salton Sea, which is the largest lake in California. And so we went down there and they developed their experiment. And it didn't,
by the way, who
was they?
Oh, the challenge. We should
the IIG West.
They were called IIG West. They're like kind of like a friendly scientific adventure team.
No, they're a nonprofit like scientist organization that dedicates their time to disproving fantastic claims of like supernatural stuff.
Oh, I see it.
They're actually an international.
The Skeptic Society or something.
Yeah,
Got it.
exactly.
Okay. Yeah.
So they issued a challenge. We ended up going out there, and the results weren't what they expected. And
really?
Yes.
If they were in the room, would they say the same thing?
Yeah, absolutely. It was not.
Okay.
I mean,
It didn't go.
There was contention, but we recorded evidence that they at first claimed was not possible.
Okay, so if I could just give you a quick explanation.
Yeah.
The lake is 9.7 miles across. So if you agree that the Earth is, they say it's 24,000 miles, or roughly 24,000 miles in circumference.
That's right. Yeah. 2 pi times like whatever it is.
Yeah.
The radius
So
4 miles.
It's roughly 24.
So 6 to 24 point something.
Yeah. So at 9.77 miles, there would be 32 feet of hidden height. So there would be a bulge of water that would be 32 feet, or I believe 18-foot bulge, but 32 feet of hidden height. So the target
somebody would
be,
have to be much higher.
Yeah, so the
like,
target would
just
be
like the
32
documentary
feet
thing.
below
Okay.
if you're looking across.
Yeah,
So
yeah.
we ended up, they said that we wouldn't see the balloons until they got up in the air, and we actually ended up seeing the balloons before they ever took off from the ground.
Okay.
Which,
again, right, there is, unless you're doing lasers, be very careful with, how you get to see things and all that stuff.
Okay,
right?
so that's awesome.
Then they
That's-
So
That's
that,
lasers.
the whole
Lasers are
experiment
awesome.
was a big contention. They actually haven't released any of the footage that they got to us. They won't share anything results that you get.
It became a conflict. They say they
Yeah.
won, we say we won, but
Huh?
we have
No,
the physical evidence.
Okay.
They have not shared any of their footage. The only footage that we have is of me actually locating. I was the one that, me and my friend Josh, I ended up locating the balloons because they didn't know where they were looking, and I used my phone, and he had a Nikon P900 camera, and he zoomed in from the other side, and we were able to locate the balloons when they were still on the ground. So that happened, and so it was a big thing. They said they won. We said, no, you're lying, and they said, well, we're not going to share the footage. So
It's very
they said,
dramatic.
prove
It's
it,
like-
basically.
It's like flat
So
Earth,
we
Yeah.
said, you know what, we're gonna go back and do it again.
Okay.
So let's go back and do it again, and let's take some lasers, and let's try our own experiment, and let's see what we can do. And
Yeah.
So we went back there. We've actually gone back multiple times now, and we went back with a laser, and we showed with the laser we were able to shine the laser all the way across 9.77 miles.
With what kind of focus are we talking about right now? Because that probably is like a massive.
Can you show him a picture?
Yeah,
That'd be cool. Yeah.
Let me show you.
Nice.
So this is all completely documented. I
Yeah.
have all the information. Dip or snack, are we sharing right now so everybody can see this? Can everybody see the screen? I think so.
Yes,
Hey,
yes,
hi.
I'm watching it. Yep.
Three different Earth curvature calculators. These are all calculators that really intelligent people design. You can put all the different factors. You have your target distance, your observation height.
Is
Target
this,
size.
do they exist? Did you make them, or are those like somebody else made them?
These
You
are
can
made-
Put them in.
Yeah,
like
these
the
are made.
numbers.
Some of these are. This is an advanced Earth curve
You
calculator.
Oh, that's cool.
You can
This
check it
one,
for us.
Metabunk is actually a website that.
check that for us?
You can redo the math for us. but
Ah,
a lot of
yeah,
it-
you can-
No, I'm
yeah,
just
sure,
saying that
exactly.
I'm pretty certain that somebody like probably already has that, like, you know, it's
Oh.
independent of the flat Earth
But
community.
Oh yeah, no, these are
that's
actually your guys' Earth curvature calculators.
Ah,
These are
okay.
your guys. These aren't ours. These
Oh,
are
okay.
like really legit.
Yeah, I don't know. I mean, I
For
believe you could do the math. Like,
Yeah.
just do you want to go through the trouble of? Oh,
Yeah,
No,
so
no,
it makes it a lot easier.
We're just
So
saying.
anyways,
Yeah.
so
So
this
you put
this
in 9
website-
miles.
Yeah,
and-
so we
okay.
put in the distance. It tells you the amount of curvature that would not be there. So 3-foot eye height, 9.77 miles. You're looking at 39 feet of curvature.
Expected
Target in height.
curvature.
Um,
If we're living on a globe.
So we did that with the laser. Here, let me show you an example. Let me show you what we actually did.
So you had it about that 3 height. The
The laser was at a 58 inches, so 2 feet short of 6 feet.
Okay.
And
2 inches.
yeah, that's what I said, right? 2 inches. Okay. So this is it right here. And we have a ton of documentation for this. This is the laser going straight across, and I'm getting different.
It's a powerful laser.
Yeah, I'm getting different angles. You can actually see the lights on the other side of the lake, almost 10 miles away, and you can see that line is completely flat. There's no curvature at all whatsoever. There's no 38 feet of bulging water in between.
So, but I'm not sure if you're saying like, so what's happening here?
So
Where
right
are you
here,
hitting?
So-
You start from somewhere and then you shoot it
yeah.
out
So
to
we
where?
started
Across the lake.
from our end. We shot it across the lake to where our friends were on the other side.
Okay.
And they also got footage of the laser coming across. It went down. It was completely from head to toe. They were being hit with the laser for sure.
Oh, because I can't see any of that.
Okay,
but
so
I'm just
I'll-
like saying,
I'll show you.
yeah.
Yeah, so
I
we're
can show
gonna
you.
have other.
I can't even
experiments
imagine,
where
like,
you can see
I'm
it.
like even wondering how is it? This is an amazing laser that can go that far
Yeah,
without
yeah.
like becoming.
Yeah. No, it definitely did. The laser did diverge,
Okay.
but regardless of the divergence, there's still 38 feet of curvature that should be blocking. So the drop actually, if you
Like
see,
an ossification.
let me just put this.
Because there is like diffraction, right?
Right.
You know,
Diffraction.
Right.
So,
So-
even if there is like the curvature as it is diffusing.
Yeah, yeah. So check it out. With this curvature calculator, you can actually put in refraction, and you can count for refraction. So we're gonna do 9.77 miles at 4-foot observation height. With refraction would be standard. So that's an extra 17% additional refraction. And your let's see. So your here we go. So bulge height. So there would be a 13-foot bulge of water in between. The drop would be 52 to 52 feet.
So what does refraction measure there? Oh, let me see below. Yeah, what they're doing. What does this mean?
Here's the
Okay.
So that laser would be completely hidden, or also it would have been up here, way above their heads, if we were shining. So what we also did was we took a hydro level and we measured the laser to show that from the source to 20 feet away to the shore, it was completely level, and we verified that with the hydro level.
Okay.
So it was completely.
What do you mean, like the hydro level you measure?
A hydro level, it's used for construction, and basically you set it at a certain level.
Yes.
What does
And
it look
it's-
like? What's the object?
The object, it's okay. So it's like it's a tub. It's like a tub basically, and there is a rubber hose that is about 20 feet long.
Okay.
So you set the level of the water, and that gives you your zero measurement. And then when, say, I want to go over here and see if this is level with this, you take it up and you raise the tube, and the water pressure causes the water at the end to level out with the set level right here. So I could see, okay, if the level's right here, this is not level, I got to bring it up a little bit more.
Yeah.
So we did that with the level, measured it, leveled it. So
How far away?
20 feet. 20
20
feet from the source. So from 20 feet
Okay,
away,
okay,
level at the end. So it would technically be with the drop. So 52-foot drop. So it would be like 52 feet above your head, actually.
Yeah, but if you're here, right?
So if you're
here,
here,
then
it would
like,
be completely blocked.
you have
That
to
lights
be-
don't go down here.
but you have to be about
Shouldn't be able to
15
see
feet
it.
high or something,
Yeah.
or what is that? 13 feet? Is
The
it
13
red?
feet is
the
the
hidden
total,
part?
the bulge.
The bulge, right?
The actual hidden height, the actual horizon will drop from the eye, bulge height. Where's the hidden height? So,
And that's the thing, right? Like that's the important thing that you did. Somebody on the other side, was you were shooting like the laser, have a camera of themselves or somebody like seeing that
yeah,
they're
we actually
like,
have
you know-
we have footage. One of our friends, she had a bracelet on, and you could see the blue laser reflecting off of it. We actually have it on film. This is all
because
well
no,
documented.
this
Yeah,
is this is
all
important, right? Because
Yeah,
if it is like flat,
Mhm.
right, then it should be like hitting you with everything,
Right, yeah.
Not
And it
just like a
absolutely,
small part.
they were all being completely illuminated in
Do
blue.
you have any image?
Oh,
Actually,
I have a whole Dropbox.
Maybe just show one.
I mean, just one,
Yeah.
because I saw the documentary and I saw all I need
The
to
thing
see,
about
right?
the
They were like,
documentary-
you
Documentary was
You-
edited to their.
Not so simple, right? Because it was not edited away from the guy saying, "Oh, that's interesting," 3 times straight. Like, can you hold it a little higher, and all of a sudden you see the moment that like the light hits.
I guess
like,
what
oops.
I guess what I mean to say is there's so many people doing experiments, and a
So
lot.
we-
But that's the
a lot
beauty
of
of
them are
science,
getting
right? You
results
have
like
to
we're
do it
getting.
once, and then if you're like, "Oops, I saw something that I expected, or I didn't expect that," and so yes, I mean it's setting up.
we had about like 30-something viewers witness the laser test happen on their trial run the night before the Salton Sea.
I'm sorry.
No worries, no worries.
So,
And what did you guys see? Oh, sorry.
What was that snack? What was that?
Oh, there were when Uber was on that night, we photographed a successful laser test. It was just a trial though.
well, yeah. So
Conditions changed much more in the morning when the dew point hit.
that was the first time we went back. So this is the time that we're actually here. We go. Here's the picture, right?
So yeah, and they've made successive trips. So how many trips have you made now there?
We've made 5 trips now.
Mhm.
So we've repeated these experiments once. And now
Yeah.
we've also done larger locations using similar methods.
We
But
just saw across from what distance did you just see this past weekend?
so this last week we went to Monterey Bay. We saw 14 miles across
Mhm.
the water. So doing all this math,
Because I think you should try something different, actually something easier than that. Because one of the things you have to explain, right, is whether the diffraction that happens, not just rarefaction,
Right.
also hitting like the atmosphere and all that
Right,
stuff,
right, right.
whether for smaller distance,
Mhm.
half the distance, say, where it has not even expanded as much, right?
Right.
You could calculate again the thing and be like, all right, can I see even for like a third, for 3 miles?
Yeah.
How much would it be?
Right.
Right. I think that'd be even more interesting. You
Yeah.
do it like on 3 mile length.
Yeah.
And if it is curved, right, then you don't even have to worry about like how big it's getting, because now you're using a brute force instrument, which is like, oh, did you see something from far away? And you know.
Right. So this is from the other side, and that's the laser coming all the way. And you can clearly see this is a low light exposure as well. So there's no, you can see all the lights on the other side. You can actually see a lot more stuff way further back. Actually, when the horizon should be 3 miles away. From So you're seeing far beyond 3 miles actually right there. So so that was the thing that you saw when we speak.
Sure. Just remember also that like even when we see the sun right dip into the sea, this has already happened like half an hour ago, right? So you're still seeing it above the horizon, and the sun is actually just gone. I mean, okay, you know, if you just, well, where does the sun even go? And, sure.
That's all contention.
Sure. But that's the thing that they're like, if it was vacuum, I mean, you have to do this in vacuum space, not a place where we keep forgetting that just because we can't see the air, it's not there. And you know, the reason why we see anything, right, there's the sky and all that stuff, is because otherwise we'd be blinded if it was coming and it was not bouncing around and getting filtered.
So the apparent location of the sun, is that provable or is that theoretical?
The apparent location of the sun?
Well, you're saying where it is on the horizon.
Worry about, like, have to go outside of the atmosphere, right? And then you can
well, that's where it would be, yeah.
So here, this is footage from what we just did at Mare Bay at 14 miles.
So what's the expected curvature of this distance?
The expected curvature here, at 13.22 miles, a 3-foot observation. I was 3 feet above the water, literally 3 feet.
No, I believe you. I believe you.
Yeah, and but my friends they had what we did was, it was daytime, so we used a mirror and we reflected the sunlight across the bay. And so at 3 feet, there would be 82 feet of hidden height. Now, taking into refraction, like accounting for refraction, there would be a 68-foot refracted hidden height. And we were literally on the sea. So I'll show you this.
Who developed this and what exactly?
This was
the humidity and all that stuff. Like, do they take that into account? Because of course, it makes a big difference, right?
Yeah. So
there's something that reflects it.
The refraction, this refracted hidden height actually takes the maximum amount of refraction that air can do, because there is a maximum amount of anything that can refract. So the water, and we've determined the refractory index long ago. So this is taking into account refraction as well. So it's back.
I definitely want to see.
Yeah. So this
you
is
perform the experiment in a shorter distance.
This is 14 miles, and there on the ground, I'm 3 feet above the water. Or sorry, this was actually not, but I have the footage of 3 feet.
So that should be
how
many feet of curvature?
That should be 61 feet below the horizon, or 68 feet.
So we're observing the water is level.
So there is no curvature. But to go back to the salt and sea thing, because a lot of people like to say that refraction is happening. That is one thing that we hear from globies a lot, is that it's refraction. That it's refraction, and it is a valuable argument, because we do observe refraction in reality.
Sure, yeah.
So in 1975, there was a study done, and this was published in the Journal of Optical Society in America, 1975. A study the effects of temperature and humidity fluctuations on the optical refractive index of the marine boundary layer. So this is the abstract, and at the very end of the abstract, it says, for cold air blowing over warm ocean air, the correlation terms was positive and accounted for 17% of the total refraction, which is what we add when we get that 68 feet of refracted. Okay. For dry hot deserts air blowing over the cold Salton Sea, the correlation was negative 268 of the total, effectively canceling the contribution due to temperature variance. So at Salton Sea, they studied it, and there was literally zero refraction going on the Salton Sea. And so this paper and this study that was done here, this is it. I don't know. I know you work at Caltech. I don't know if maybe you can get your hands on this document. from the Journal of
I
Optical
see what
Society
you're
of
saying.
America.
Yeah.
Because all I can do is read the abstract. You have to actually. It doesn't have
okay.
the actual document, but it would be
How
nice
long
to
ago
see
was that?
This was in 1970.
Oh, that's a long time ago. Yeah, so you can't just download it. Okay.
I mean, you can download. It's
If
like
you, no, I know you have to pay.
You have
which
to pay.
is BS.
I have kids. I have kids. I can't afford to do that.
I understand.
But this study, this is when they actually well, I don't know if this is when they developed it, but they have determined these refractory index rates. And they actually went to Salton Sea and said that there is literally zero refraction here. And so that gives our observation a very valid point.
Yeah.
It kind of validates what we were doing there.
I want to see what this paper is about.
Yeah.
Because I want to understand what this negative 268
That's what I said.
of the problem means.
Yeah.
Right? Because I think that the 17% may not be the max. Right?
Well,
even though it seems like it may be actually much higher. You know, the same way it's like a
then we-
mirror, you can see
We
anything
should
you want.
definitely give him the
So, yeah.
opportunity
Yeah.
to
So actually,
we
you
should
can email
definitely
me
look
that
into
one so I can check it
Yeah, we should
out, but
definitely-
also I
yeah.
can send you some of
I'll
that.
give you
I would really
a-
like to see that.
Yeah.
document.
But
so
it
that-
seems you've already done like a lot of work.
Yeah, absolutely.
My suggestion to you is you make it even simpler. You
Mhm.
test the simpler theory, okay, to get rid of the refraction and all that stuff as well, right? 3 miles. If you put 3 miles in there, what would the height be? Something where you can be like, all right, let's just get a mirror to reflect it back. If it is flat, you just keep it there. If it is not, then you should be able to do maybe it's 5 feet you need to go up, right?
Yeah, what is 3 miles? Is just a
It
little
should be a
bit.
third,
It should
right, or
be
something, or
almost
whatever.
like a yard or something, no, more than a
Let's
yard.
just do 3 miles, yeah. It doesn't sound like much, but
It's
again,
8
3
inches
miles.
per mile squared is like
Oh
the
my
rough
gosh.
estimate.
If we're
Yeah, there we
if we
go.
had a 4 foot
Yeah.
6 feet.
6 feet, so that's not that much. 3 miles, about the height of a grown man.
So if we had 2 feet, like you'd have to be 2 feet higher, right? So if it was at 4 feet living and you had it at 4 feet,
Yeah.
it wouldn't come back unless you
I mean,
lifted it 2 feet.
Of course, we like these really grand experiments because
Oh, no, sure.
there should be like a mile, and
This
it's not
is,
there.
I know,
Like,
but this is the thing with
Yeah,
science,
so-
right? We do
so
that too.
if-
You start with the
if we-
biggest thing and then like, what's the smallest thing? And you
Yeah, see, even at 3 feet, it's 0.29 feet with refraction and 0.52.
yes.
6 inches.
So
So
then
what we're
say
trying
you
to
do
look
6
for
feet.
is-
yeah,
is-
6 miles.
I mean,
6 miles.
6 miles.
6 miles, I think would be better.
I mean,
right?
we
I think that's what
we've
the-
done. So what we're doing
the
is
other guy did.
we have repeated this, and we've actually got the results that we were expecting to see, and we've repeated it multiple times, and we will continue to
Yes.
repeat it as well.
It is.
And
You don't have to continue repeating it. You have to remove. That's what science is
remove
all about.
variables.
Remove variables.
Mhm.
That's the hardest thing, right?
Right.
Well, I told you
It's so
also
hard
like
to do it-
the
do it
gravitational
outside
waves
in the real world.
That's right.
You
They-
have to deal with it.
But this is.
Really-
But this is. I agree.
Mhm.
But this is what experimentalists do, and that's why they're so ingenious. They're like, what is a representative? The smallest thing I can do to verify the theory, and then build on top of that. Then add even more. Then add refraction. Then add all the other stuff. So do it instead of 9.7 miles, where it's too high for you to just test, like with a mirror, right? Do it at 6 miles, where you're like, all right, I need to put the mirror at this place, but if it is curved, to reflect the laser light back, I need to, the predicted, according to the ballers, is like, I need to move it 3.5 feet, exactly, right?
How-
Test it, and then if you see that it's coming back, you're like,
I would.
I mean, when
That's
we're
what I would do.
so another thing. that-
because otherwise refraction, like even if you're saying all of that, then you have to do a whole other experiment to convince anyone, right? That says this is exactly how I measured the refraction, and it was below the level, and so it wasn't possible.
If
You see?
Nathan wanted to start a dialogue with scientists about his research, how could he do that?
Do a little break, come back with
Okay, you want to take it?
What time is it?
panel questions.
Oh, it's 8. I may need like in about 15 minutes dinner with.
Oh,
Okay,
girl.
I was
No,
gonna.
yeah, I had.
Well, we want to give you the panel.
Yes.
you there?
But
So
you have my email.
Yeah, I'm gonna give.
And
I'm
we're
gonna give you
we're
your
out there and
email.
we're doing these
Yes.
experiments. We keep getting the same.
How far away is it from here?
What? Salton Sea?
Yeah.
Oh,
So,
it's about an hour and a half drive.
Oh, okay.
Yeah, it's
Like
towards
north.
Coachella Valley.
Oh, okay. Coachella.
You guys are
Okay.
maniacs. They drive everywhere. for
Yeah.
this stuff.
And we
Okay.
just drove up to Monterey. It's like freaking.
Yeah, yeah,
It's
yeah.
like 5.5 miles.
Have you talked to
Sacha,
the kid that did the
you wanna jump in,
documentary
Sacha?
experiment?
I haven't personally,
Okay.
but
Definitely, because he was also out. I don't know, he was out there or
yeah,
whatever.
he went out there with him. But what I wanted to do, is like I said, I trust what I observe.
Yes.
And
I'm with you.
And I've collected the
Yes.
data, I've collected
Yes.
variables,
Yes.
we collected humidity data, temperature,
Yeah,
everything that you would need to. And we've done legitimate scientific observations.
Yes.
And it's all been documented.
Yes. The problem is the
And-
variables.
Right.
Right.
I'm gonna
That's-
set you up with the email. and
That's
he's
the
gonna
problem.
help
Like
you,
it happens all the time in science, by the way, what you're going through right now. Where like you have, and the only reason why you, and you said like, you want to be scientific about this, right? The only reason why you have to worry about someone like me saying, well, there's more variables, is because you really want to know what you're seeing is not due to flatness or absence of curvature, it's because of refraction or like mirror reflection or anything like that, right? That's science, right? Because there is a preponderance of other evidence that says, well, yes, this happens and all that stuff. Exactly. So you have to remove the variable. And by doing that, you'll be doing like serious, like cool
Well,
science.
Would you be interested in perhaps collaborating with something?
I'll be honest, like it's not because I don't want to come out like 90 minutes away. I'm so busy.
Oh no, I totally understand.
What I can
But
do though,
intellectually-
yes, of course, what I can do though is like give you that suggestion. Try, you saw it in the documentary, but you were connected with the FE core, right? What did they try? Go see if you can repeat that, if you can see anything else, because they tried something pretty much similar thing, right? But they had a reflection, they had a mirror, so that from your side you could see, like you throw it and then you could see if it really hits, comes back, and if it.
Have you guys discussed the infrared images we've been getting lately?
Hang on, Jibby. I was just gonna ask him.
All right.
I'm gonna give it to them.
Okay. All right.
Go ahead,
That's
panel.
cool.
Thank you. I'm gonna
What do you got, panel?
Thank you guys.
Hi,
That was
can you
really
hear
cool.
me?
Yeah.
Yeah.
Hi, Spiros. I want to thank you for your time and coming to the show. I really do. So I'm a magician, and the first thing I realized was I've been fooled. I'm not spinning, and it took 10 minutes for me to realize I've been tricked. From that point on, my research proves that there's no peer-reviewed paper that shows that the Earth spins. However, there are 4 experiments: the Sagnac experiment, the Aries failure, the Michelson-Morley and interferometer, all prove that the stars are moving, not me. That places me, you, and every one of us at the center of the universe, which I find quite important. The cure to cancer would just be removing fluoride from water and toothpaste. That would pretty much cure cancer. I've got a problem with Venus at night time. I see it most of the night, all of the night, and it shouldn't be because it's in lanes 1 and 2, Mercury. Water's level, and that's because the Earth's not spinning. The deepest hole is 8 miles, so nobody knows what's in the center of the Earth and the mass of the Earth. And that brings me back to the question I want to bring to you is the theory of gravity. M1, M2. If I'm measuring the sun M1 and Earth's M2, then all other forces and smaller masses are cancelled out.
Sorry, what do you mean?
Well, M1 and M2, it doesn't account for M3, M4, M5, M6. Everything else is cancelled out when you're measuring only 2 things.
Are you? Oh no. Are you saying that we don't measure like the mass of the humans or everything else on Earth, or just?
No. You can't.
No, I think he's talking about Newton's law of gravitation.
I'm talking about inside of it.
Mass of 2 bodies for gravitation.
Yes. And what happens? Like, how do you? Are you talking about the 3-body problem? Like, what exactly is the force or how?
Well, in the law of gravitation, you're not accounting for all bodies.
I mean, you can always just add up all the masses, right, and say, well, it's not.
But how do you know those masses?
I don't know, the way you know that how much you weigh.
No, the mass of the moon, the mass of the sun.
Yeah. You're saying the mass. I guess we're going back to the same thing, right? To that,
You're measuring something by looking at it.
That's right. How do you know that the person next to you, your wife or your kids, right? Weigh 30 pounds, right?
But I might have 100 pounds of stuff in my pockets. You don't know.
Well, that's right. And so you wouldn't know about that.
Yeah,
I completely agree.
you might
But
not see it.
the idea is this, and this is again what science does, right? And we don't have to take any of that for granted. But if you have a theory of how everything gravitates towards everything else, because of locally you've measured it, right? With your friends, with everything around you, you've done all these experiments, the Michelson and Morley and whatnot. And you're like, all right, this seems to work no matter how small or how big it is relative to our scale, okay, not planetary scales, right? Then you extrapolate, and you're like, okay, there has to be a miracle, right, for this equation to stop working for something that is like, say, twice as big as a house, or 10 times as big as, at which point should the law of physics, that particular one, stop working? And what is interesting about this is that you wouldn't be wrong, okay? For certain things that are too big or too small, other laws of physics end up appearing. But it doesn't mean that that main law of physics for certain scales, right, that ends up becoming completely invalid. It just becomes less and less right, whether you become too small or too big.
Wait.
But even deeper into science, right? It doesn't say like, oh, now how do we know? It's like, well, we want to know, right? We want to go deeper. As scientists also, we want to know the problem ways and how much like the sun weighs and stuff.
Okay, excuse me, but you just said that like we observe gravity like on a small scale.
Yes.
Where do we observe gravity on a small scale? And like what, I mean, the whole Apple thing with Newton and stuff like that, that would be the only example I can even think of that was brought up to us.
Yeah, there's a lot of cool examples. Actually, who brought up Michelson Morley?
I did, Spiros.
That really,
Poncho.
yeah.
I'm Poncho.
Aries failure.
This
The
is like
Shannon
common.
atmosphere.
But you
We're all
should-
very familiar with this.
Yeah. But this is like a great experiment, right? Where you're measuring something that's like almost at the microscopic level and how much it weighs as like, a drop of oil, like, moves through. So these are pretty interesting experiments, They're very ingenious, I guess. People didn't know what to expect when they were doing them. They're like, there's stuff.
Well, when he tried to measure the light through the water, if it had refracted, he'd have had to place the telescope in a different place. And he didn't, which meant that everything above him was moving.
Oh, I mean, hey, by the way,
Yeah, well,
if it's all about that, you're right. But like, you can imagine that either nothing above you is moving, or that you're moving, right? Or that you're stuck and everything else around you is moving. It will look exactly the same. And that's a very deep idea. That is the deepest idea in the universe, that everything is relative to something else.
But
right?
we can never verify what is being observed in a place where we aren't ourselves.
Of course we can. I will actually prove it to you right now. Okay? You and I are not actually looking at each other directly. If we turn on lights here, we are gone. If we actually isolate acoustically from each other, so phonons, vibrations of the air, right, cannot reach each other, then we are even further apart from each other. The only reason
See,
why...
Poncho, I told you it was a VR.
The only reason...
don't start with your VR, GB. He's the creator.
Because of all from electromagnetic waves to like, phonons, to all the vibrations, all the things that are happening that are echolocating us here. And we have the illusion that we are not millions of light years away from each other. That's it. Because there is a way for us to interact with each other, never directly. Even if I do this, I am not actually hitting my hand. You never touch anything, okay? It's electromagnetic repulsion that creates even like a vibration.
As flat earthers, like, we're anti-relativist. Like, we don't believe in relativity. We don't agree with relativity because
what part?
What part?
In what part of it?
In the
Because
part
it's a
that-
framework. It's not even
Right.
like.
We'll say special and general.
Okay.
We don't agree with space being a vacuum. We don't, because that's what Einstein did. He removed the luminiferous ether and replace it with the void of space.
Well, we should go into what space is, because it is a quantum vacuum. And yes, it is not a vacuum for sure. It's much more complex than that, and that's where space also comes
Well,
from.
I mean,
There's stuff
so
underneath.
what we try to stick to is what we can observe. That's what we're up to, is what we can
But remember
observe,
what I
we can
said?
measure.
Remember what I said? this is the most dogmatic aspect of, you're the most dogmatic scientist actually, which is hilarious to me, right?
I mean, it's the
And
basis of the scientific method.
I agree, but
That's
remember
how
what
you
I
get
told you?
started.
Remember what I told you? That there is a full circle. There's
Right.
not one like the
Right.
12 o'clock point. And that full circle is what allows it to be bigger than religion
Right.
and belief. There's a big difference between religion and belief in the
Belief
scientific
is-
method.
Belief is the enemy of knowing.
And no, I disagree. I disagree with that. I disagree with that. I would say that belief is the fuel that makes us humans want to know. If we don't have any reason, right, to want to know, if we don't have any stakes in this, you're not, if you don't start, that's the beauty of science, right? If you don't want to prove something, you want to prove that the earth is flat. Guess what's going to happen the deeper you go? You will find out that the earth is either flat or it's not flat.
Right.
And the question becomes this, on your own personal journey, do you have the integrity to follow the path where it takes you?
Yes,
And tell us from your side as well, right?
absolutely.
We believe in love.
But that's
all
no,
that.
forget even about like whether it is a globe or not, right?
What is
It is that journey that matters above everything else.
That's why we
And this is the toughest
Spiros.
journey. Being a flat earther is it's all uphill. We
Yeah.
are outnumbered.
I'm with you.
We are outgunned, and we are outfinanced.
Yes, but I would say this: scientists as well in this era are also outnumbered, right? A scientist is like what? There's like maybe 1 or 2% of humanity that is scientists, right?
Aren't we
The
all
rest are like
scientists?
industry.
We're all scientists.
Sure. No, hey, I'm
We're
with
all
you. But as
scientists.
far as like, you know, making this your life work, right? Where you're like really going in there and you have a bunch of people that yell at you like, no, this is not right, and like, and you have to prove them and all stuff. Exactly. So that and that journey sucks. Okay, really sucks. You don't get paid well at all. Okay, like you know, you don't get respected or these days, or even or you're not a celebrity. You know, you don't like
I
just
got
go.
the love of God, Spiros. I got the love of God. That's my payment. But the test that Nathan's done was based on a heliograph test way back in the 1800s, 125 miles. The world record microwave, 146, which has just changed to 343 miles, direct line of sight. This is the microwave, it's direct line of sight. And then on top of that, we've got Jay Tolan's infrared video that shows us 1,200 miles, no curvature, Spiros, all the way from Vegas to Hudson Bay.
Not Vegas, from
Today, I told you I'm a magician.
It is 20%.
You guys are the best. Very cool. Well, thank you for having me.
Oh, thank you.
Yeah, no, you guys are an awesome community actually, and very, very curious. That's what I also said in the documentary. But again, I'm not going to sugarcoat it, right? Because I talked to also some of the flat Earth community after the documentary, and they told me after I said like, all right, so the experiment, the gyro, right? You guys came up with it, and you did this, and you ended up seeing. No, I'm saying the FE core,
Yeah,
where,
but they're
you know,
not
within.
the same
I know.
as- yeah.
You don't want to. It happens in science too, right? You know, where you start having your own fractions,
We
which is
are.
good.
We
Which is
have
good.
a lot
You're
of
testing
that.
each
I mean, it's
other.
good to be
This is
the
you're gonna have your own
company.
intro peer review.
Diversify.
But when they saw, and at least, and that's where I will end with. But like when they saw 0, right, or when they saw 15 degrees, and they didn't see 0. For as somebody who is looking for the truth, right, not with some other agenda, or they want it to be 0. No, I mean, yes, as I said, you always start science, you're like, I want to be 0. I want to be 0. I also wanted to solve that problem. I had ideas, and it didn't pan out. Something else panned out, and it was true.
I mean,
And they see 15, right? What do? There is a choice as a human being. And there is a deep choice at that point, right? You can say, okay, I have other reasons to believe that something else is going on, so I have to go deeper, right? Yes, it is 15, but maybe I was wrong about my hypothesis because I was using their theory and all that stuff. Then you do the laser experiment, right? You're like, all right, at least this, right, will work. It didn't work, and it is again on camera, it is all that stuff. And then you keep going deeper and deeper, right? At which point do you trust others, and more importantly, do you trust yourself?
I
right?
trust the mechanical gyro, Spiros.
Mechanical gyro.
It was a mechanical one, not a digital one.
Paying $20,000 fee so quickly.
I
don't know.
Like I said, we've
Yeah.
been doing these and we've been observing the same results, and so we're going to continue to do it. I would love to collaborate with you.
I will say this. I will say this. Here is, I will end with this because it goes back to empathy, right? Do the other thing. Do the opposite of what you've been trying to do.
Test against.
Exactly. Try to prove that the Earth is not flat.
We've done that. That's how we became flat earthers.
No. I don't mean go and find evidence online and all that stuff. Because what ends up happening, right, is you end up focusing your mind to finding evidence that is against the Earth being a globe, right? Trust me on this one. Guaranteed, okay? Because there's a lot of evidence out there. A lot of pictures, millions of pictures, like, but then what do? You say,
well,
no proof.
Are you,
Evidence, but no proof.
no, I don't trust the NASA, and then you always say you don't
but Spiro, are you saying that like the observation that water's level is inductive reasoning of some kind?
Sure, but I just want to say that when
for us, it's counterintuitive that it would curve.
L is like, I don't know what they're doing, right? All these people.
Spiros, to be honest with you, like, do you know what it would be like to want to join a club where everybody thinks you're crazy? It's not really like an attractive thing. Like, we've come to these conclusions based on like a lot of work we've done, not just like videos we've saw.
Yes, but right, there is a way to do a lot of work and always get to the same conclusion. There is a beautiful, I think it was in the New York Times or Slate or some magazine, put this interactive thing on their website where they asked people, right, to figure out what the pattern was. They wouldn't tell you what it was, but you could guess. You had 3 guesses to figure out what the pattern was, right? It'd be like 7, 15, 21, whatever, and all that stuff. And most people would get it wrong because they thought they figured out the pattern, and then they ended up they would put in their own numbers to test if their theory was correct, right? And then end up putting numbers that fit the pattern, and every time he said yes, right? They never tried something that would not fit the pattern. And I went through the same thing. I remember oh man, this is the pattern. And I'm like, why don't I try 14? And then it fit the pattern too. I'm like, what the hell? And then I saw the bigger picture. I'm like, oh, okay.
We all started with the assumption that we live on that globe. We didn't start with the assumption it's flat. I'm
sure,
1 in a million did. So we all started with seeing, wait, can we prove the globe? And that's the basis of all of our research and experience and journey. And at some point, we came to the realization that we can't. And
but
then
what
we
if
started
you were to do
go,
these smaller experiments?
So you're seeing
yes, and that's what I'm trying to say, right? If you're trying to prove something, or if you're trying to prove something against it, it changes the nature of the experiment you will end up designing, right?
So,
for example, if you're trying, because what you're doing right now, you're shooting a laser or the sun, right? And it's brilliant, but you want to see the light, literally, right?
Well,
you're hoping, even though it's far away.
I wanted to see what I could see.
Exactly.
That's what I wanted to see.
But
I wanted to see what I observed.
Yes.
But
yes.
even if he wants to see the light, he shouldn't. That's not going to make him see the light. He's going to try to see the light, and then he can either see it or not.
No, I agree.
Come on, man.
But that's my point, right?
Yeah. We're not trying to see the impossible. We are seeing it.
I'm with you, but it gets subtle. It gets subtler than that. That's the problem, right? Because then you have to remove, as we said, all the variables, all the reasons why you would be seeing the light, even if the Earth was curved, right? And then you have to be, okay, I have to now try to disprove that the Earth is flat or that the Earth actually is round. So what do? You go smaller distances where you don't have to worry about refraction as much and stuff, more direct back and forth, right? And then you test it. Not the longer, the more impressive one, but the shorter one. And then you see what you see, right? And if you see you don't even have to raise at all, and it's just straight.
So to you,
you're all right.
So to you, a
shorter
distance,
because it's still even if there is still, yes, of course.
So if I did,
there's no parallax, Spiros. There's no parallax in the stars.
That'd be more interesting.
Of course, because you have gotten rid of the diffraction issues and all other stuff. And in fact, that's what that kid did, in the documentary. He did the shorter, I think, 5-6 miles. And then at this point, his friend on the other side was like, all right, I don't see anything. He's like, all right, could you raise your hands a bit, above your head? And the moment he does that, like, shoop, comes right into focus. And you're like,
you know, like I said, I haven't even seen it. So
but yeah, I know. But that's why I said, like, a scientist, that's what we do as a scientist, right? You go and you talk to somebody else who did an experiment. You're like, all right, I want to collaborate with you. You just found this interesting thing. I have a different theory. Something is strange here. Let's figure it out.
So, having seen that, does that kind of open you up a little bit more to the idea of the possibility?
I will tell you, I'll be honest. No, there is no amount of evidence, and I will be dogmatic about this, right? No amount of evidence.
Well, you agreed that we're moving at these tremendous speeds.
I want to clarify though why I'm saying this. It's because above even observation and even the scientific method for me, given also my research, right? I believe in people. Okay, the reason why I'm here is that, right? Whether you're right or you're wrong, in the end, it will be your personal journey, and it'll be that adventure is the best part of it. It doesn't even matter. Does it even matter whether the earth is flat or round? No, it is the fact that you're part of the community now. No, but
that's pretty deep. Yeah.
Do you think all the experts should keep their jobs, Spiros? They're wrong. If all the experts are wrong, do you think they should be allowed to keep their jobs?
No, I want to say something else, right? Like, this is a serious question. Does it really matter? Why does it matter to your personal life if the earth is flat or round?
Well, that implies they're lying about so much more.
Exactly. So it comes down to this. It comes down to, like, what else are they lying about, right? It is a more global. It's not personally in your life, right? It's not going to change the fact that you work and, like, you do the stuff you do every day, but to maybe, like, oh, what else is happening, right? You start getting suspicious about stuff. So it goes back to what I said earlier. For me, right, I try to see the best in others. So I hope that they can do the same for me, right? It's like a mutual relationship. And the moment you let go of that, even in the documentary, Mark Sargent, they ask him, right? So who do you trust? And that's what it comes down to. I'll be honest, right? For me and for your community, that's what it comes down to.
I trust myself.
Exactly. And this is what Mark said. And I found that, to be honest, sad, because his mom was around him. Patricia is her name, right? They become friends. I'm sure he has other people that he really, he gave a very nice speech, like at the convention and all that stuff. Thank you so much for being here. But he doesn't trust you. He doesn't trust anyone but himself. And
we are all like that.
But that's the thing, right? It is a choice, because I will tell you something that may shock you. You're all right to not trust anyone but yourself. I'm not joking even about this, right? You're all right. And the irony of it is, the reason is relativity, okay? No one has the same view of the world, the same observation, unless they're exactly the same person and they can see it from the same point of view.
From your point of view, you're the center of the universe.
That's right. And everybody else is kind of out of it, like, and around you, and then they don't get the picture you get, right? But how can you ever have a relationship with anyone? How can you even have a community?
I feel love for the world, and I feel love for people, and I don't have real anger about this. Actually, I have so much curiosity, because and it's so interesting.
Yeah.
And I give it the benefit of the doubt. I don't know the motive, so I'm not like, they're trying to control us. I don't know what they're doing.
Because there are kids, like, growing up and then go through school, and then they go and they start working at JPL, and they have no idea. They're even thinking about, like, I'm going to test if the earth is flat or a globe. They're like, I want to send a freaking rover to Mars, right?
Yeah.
And, it's like, I'm going to do it. Or they do it. Okay, I have friends who did that. And they're engineers. They're not even thinking about equations or, like, what's happening out there. They're like, they're doing it. And I don't want to be the kind of person that says, like, I don't trust you. And I don't trust you working like a Genentech or for cancer therapy. And I don't believe that, like, it is so hard of a problem, and so on and so forth. It is, in my mind, more important to believe in each other, because it is hard. Everything is hard, okay? It's not so simple. And to appreciate the journey, right? That adventure that you're going through. Like, I love this community because you're going through an adventure. And yes, it is crazy to be part of the community unless you really want to, like, figure something out, right? You're not, welcome in most parties.
Well, thanks, man.
Sure. Fine. why I'm here.
We're so happy to talk to us, and we are really okay with that you don't agree with us. Like I mean, of course we love it. We love but we love it that you're listening to us and talking to us and exploring. It's just so meaningful, and we hope that we can have more conversations and other flat
Oh
earthers.
man, this has been great.
We hope you had a good time.
Sorry.
Yes, yes. Okay, I'm getting
I can listen to you for
I'm
hours.
so happy. I'm so happy this keeps moving. I think we could go on another 4 hours and keep it interesting.
That was
Keeping interesting.
So yeah, how
know,
much do you
and that's
want for
awesome.
a round 2?
Talking and
Yeah.
figure stuff out, you know?
Yeah.
Throwing out ideas.
I want to keep up, like, with some of the progress, some of the things you're working on.
I mean, if you
and
want to see
again,
in 6 months,
less is more. Less is more. Yeah. Because that's I figured out, like, from my own research, and as a mathematician and mathematical mind, the one thing that this advisor of mine taught me, one thing was less is more. In mathematics, the first thing you do, right, is to figure out, like, how everything is connected, generalize, and be like, figure it out. This is the pattern, right? He's like, no. In physics, you do the smallest possible experiment, either thought experiment or actual experiment, that could give you the smallest piece of evidence that you can use, maybe to amplify it slowly and build bigger and bigger, right? And it's so hard to do that because you need to understand the essence of something, right? What is the essence of gravity? If it is a thing, it is not a force. That's what I want to leave you with, right? It is not a force. Yeah,
I believe it.
And it's like,
I know.
but it is something deeper.
Right.
It is a concept, right? It is a concept of freedom. That is actually what it is. Gravity.
So gravity is a concept.
It is a concept, and everything is a concept.
Beautiful.
Space, time, the laws of physics, the fact that we think we are all alive and talking to each other are concepts within a data structure, a quantum data structure.
Like it's a virtual reality.
Shut up. It goes beyond. It goes even beyond. It is like you wouldn't know you were in a virtual reality system with the way we're going, right?
Unless we could figure it out.
You go beyond the matrix. That's what I do every day in my job. The tools, the intellectual tools, allow me to go beyond physical reality, right? Because you can imagine unicorns when none exist, okay? And then you can test it and figure out what is possible. And that's what I love about the work that I'm into right now, that everything goes. Everything is possible. But you're not going to say that, yes, there is no gravity and I'm going to jump from this building and I'm going to be fine. Don't do it.
But if everything's
Don't
possible,
do it. Yes.
Thank you.
But that's
possible.
but that's why, and this is a very subtle point. Everything
Start flying from the ground.
that there is this reliable rules and all this stuff, right? Everything is possible, but some things are much more likely than others, depending on your point of view.
Well, there's a constant physics despite your point of view.
No, that's the key. There is no constant physics despite your point of view. That's the thing that.
Well, jumping off a building. Despite how many drugs you're on, you're going to fall.
Yes, but there is a 1 in a trillion chance that you're not.
Has that ever been?
And that's the one.
Can you make that mean that
The same way.
guarantee?
This
Can
way.
you guarantee there's a chance?
Yes.
Tell me there's a chance.
Yes, that's right. Chance. But this is. But this.
That experiment, less is more. Jump from 2 feet instead of
Exactly, and I start. But this is.
There you go.
But this is the beauty of this, right? Like, how the heck we reverse engineer reality with its, like, it has manifested all these rules that we didn't ask for, right? We're like, what? All of this exists without us having created, like, and make it and make sure that, like, things are moving and all that stuff. So how can we reverse engineer? The answer is actually science, right? We've been doing that for a couple thousand years now, since the ancient Greeks decided that we have technologia, right? Which is like, we are allowed as humans to manipulate nature and try to reverse engineer it. And start with fire and a bunch of other stuff, like moving. And all of a sudden, we can do something that is pure freaking magic as we speak, okay? I'm talking with somebody from Britain right now. Hi.
Sacha!
How the hell is that even a thing? Okay? This is like I'm not even holding
Because it's
anything.
across the flat plain.
That's right. Like, just but isn't that amazing?
Keep it level.
It's amazing
man.
the satellites are faster from here to Britain.
Ross. The transatlantic cables, they run across the seabed.
Yes, no, but
That's how we're talking, yeah.
But no, the satellites are faster from here to Britain than they are from here to the ISS.
Matter whether it is because of the satellites or Wi-Fi or there's transatlantic cables, which there are, right? The fact that we figured out how to do it is the insanity. That's how we reverse engineer reality, because
That's creativity.
150 years ago, if we were to try to do this, because we are still human, we still have aspirations to speak with somebody from Britain about how the Earth is flat potentially or not, we would be like still talking about it and be like, all right, there's 1 in a million chance that I can read their thoughts right now and do it for 3 hours. Here we are doing it.
Did you tell your friends that you were going to meet with flat earthers, your colleagues?
I have told one person who is my office mate. I was to call the police.
Call me at 9:30. If I don't answer, call the police. Send them this
That's like,
check
it's
my.
so great. He's not, he's coming back. He's not bringing flat
That's also the
earthers.
difference between men and women too. Right? I was thinking about that. I'm like,
Especially if you're a big guy.
yeah, I'm not right.
Are you going to tell your colleagues?
Oh yeah, I mean, I've actually called
you
Vance and they
have?
like, it's a very nice thing. I'm like, it's the right thing, right? We need to
It's
communicate.
so
We need to
cool.
talk.
Thank you, man.
It's been a pleasure. You guys have been awesome. So nice
So, any
meeting you all
questions?
across the globe.
Any last question?
Yes.
Oh, do you?
Spiros, it was nice to meet another magician.
Nice meeting you too.
We'll end with that one, right there, right?
Cool.
Awesome.
All right, Spiros.
We'll stay on, man. You guys carry on.
This is, yeah.
You guys can hear us packing up and kind of hanging out for a bit. I think I'm gonna have a beer.
Spiros, you're
Oh,
amazing.
look at that.
It's been so positive for me. Thank you so much.
Thank you for having me and presenting.
Here's a song for Spiros, and now it's time to go.
Great pleasure meeting you.
It was really loving having you on the Flat Earth Show.
It's a lot to talk
5
about.
hours because
You tell your friends.
fascinating everything about you.
It's a conspiracy.
It's a conspiracy. No, this was a great 2 hours.
And I kept my word. I didn't say those 2 words in the sentence.
All right, awesome.
Thank you, Spiros. Thank you very much for your time.
I'm good. Thank you guys.
Yes.
I know how they're gonna reverse Thanos' snap. It's gonna be Ant-Man. He's gonna go in the past. He's gonna catch a time portal. I heard us say it. Spoiler alert, everyone.
Yeah, he teleportation, time travel. Yeah, he kind of.
Yeah, he can't say, but we know.
So,
You know.
do you guys think we gave him enough points to really stumble over the rest of the night?
I got $50. Hoping he gets a round 2. I hope dude offers some money in the parking lot. No, I put that out. in the
Better than
chat.
a gas station
I'm
bathroom?
serious. Well, it's 10%. Can you guys come up with, $50 each? Shit, I'll charge you out of my card. I'll do 100, whatever. I want round 2, man.
Yeah, no, dude, I would pay for a round 2 with that guy again.
Well, that's what I'm saying. This is better than cancer.
Dude, and Sydney was actually saying that we should invite him to one of the tests,
He said he was too busy.
but he said he's too busy.
I said thank you.
Yeah,
Yeah.
I wouldn't want to go either. I wouldn't.
It stinks of fish, doesn't it?
Not to the Salton Sea, dude. One of the other ones.
I'm sorry that I didn't.
There's other ones that we can do.
I don't blame him.
Thank you, Sasha, for hosting.
Oh my God, it's the first time I've ever done anything like that.
Sasha, you're fantastic. Thank you.
Sasha's the best.
I wanted to give you guys more time. I wanted you to.
And I didn't say
Yeah,
bendy water.
Sasha, that 20 minutes we got was awesome.
Thank you.
whatever it was.
Yeah, something like that.
Whatever it was.
17 and a
It
half.
was VR. Shut up, GB.
6 pi. I don't know how much time we got. VR, dude. Did it come out VR? A ball or flat tonight? It came out
Right.
VR.
He thinks he's living
Done.
on a ball and he's talking about VR with you. Yeah, you're both in La La Land. Shut up.
I win.
Don't win. There's a baby Jesus and God loves you.
Oh, also thanks to Nathan. Thanks to Flat Earth Dude. Thank you to other guy who I'm sure. Sorry.
The other guy. You sound like
Dude.
Joey Rusher. What's his name?
Whoa.
Snack? What's his name?
Snack. I don't know the guy's name, but he's the NASA dude from the.
He's the NASA guy, right? Yeah, he's the
Yeah.
the
Flat Earth
Pippin
Hollywood.
astronaut.
Yeah.
He's the. Thank you, Kenny.
You
Cheers,
guys
man.
did
Job
fantastic. This has
job
been
well done.
amazing.
That was pro.
Yeah. That was actually very pro.
Bro, right?
Yeah, shout
That was
out to you
so
boys.
pro. That was so pro.
I was on my best
That was great.
behavior.
Yeah, you guys think
Yeah,
Yes, we
yeah.
all know
That's
you
why
were
we
a
only had
punch.
20 minutes. We had to get crazy in 20 minutes.
Chat, we're not on your best.
Hey, and you know what? Nobody heard my torch once. So don't give me shit about that.
I was not watching the chat at all. I hope everybody's okay. Nobody
Oh,
lost
dude,
an
I
eye.
was. Jibby was.
I thought it was really awesome.
Oh, I knew somebody would be.
He was like, I can't believe this because it would mean not trusting basically all his colleagues
Yeah.
and everything. And
I mean, what he
it's really
did there
meaningful that
is
he's
it-
like talking about what he's walking him.
you know that and that is another logical fallacy is appeal to emotion.
I was having trouble with this dribble. I kept zoning out, dude. I kept doing other shit.
Yeah.
Well, I
know.
mean,
I
Uber,
think
try to imagine, right? You can lift something and weigh it. Now, take that and imagine.
Completely forget about it,
Oh,
and then
yeah.
come back.
I had a couple snippy lines in there. I didn't really mean to do it that way either. It's just kind of, yeah, it just happens. I said it. I guess I was just trying to.
Yeah.
It's a lot of stuff.
You did so great and you presented such good evidence. And
He's
you,
a really likable guy, man.
isn't he?
By the way.
Yeah. You're very like a sweetheart.
My
You're a
wife's
sweetheart.
like,
Well,
my
he's
wife's
very
like, I like him a lot.
I told you guys you were
I go-
looking.
I go,
Like,
can you
very
count how
nice.
many times you use the word period, please?
He's
I like
straightforward.
Yeah, you guys, I don't know. I would have probably went with Matt Powerland's picture of painting and just left it there the entire time. That's just me.
Yeah, but then we might get like copyright hit by.
That's what
freaking
I'm
Matt.
saying. Then he could own the hangout.
Put
And...
it in from the camera. Should have put it on top of the camera, Jimmy.
Hopefully,
Well, I think,
better.
yeah, and I think it was a success, and you had a good time. I think that you know we weren't here.
We never got violent. We
Yeah,
didn't hurt him or anything.
No, look at you guys. Ragtag Bunch doing a great studio little setup. I mean, it was awesome. I mean, he probably feels like I should have got paid. But yeah,
What
No,
for
it went
lying
great.
to us? Shut the fuck up, Jimmy.
it went great. It went great. No, he did a lot of sci-fi writing. Try to imagine. Okay, what
Try
if?
to imagine, yeah, I imagine you're full of shit, Jimmy.
Try to imagine now. What if I imagined that you were
VR. I'll
possible?
imagine VR just for you, Jimmy.
But we are like, you know what? We're here because we're thinking about it. We want to be here.
Well, I think the
Perception's reality, apparently.
fundamental mistake that I think he made.
I did agree with him on a lot of things. I got to tell you.
He has some really
Hey,
good.
so Snack, is it
You
okay?
I already
to,
said what I agree with him about.
Just kick him off the paddle, Snack. He's doing McSweden.
Hey, Snack, is it okay to post the hangout link in the dispensary now?
Yeah, we're good now. We're good.
I would start a new one if I was you, Snack, as well.
No, we're good. We're good. we should end this and just start a new one, but
Uh-huh.
it's up to Snack. But
Well-
that's what I would do. From the me and Flat Earth Charles went 8 hours, but we had a 3-hour debate. Probably cut it short and start a new one.
Well, can't you do that with without ending the hangout call?
Yeah, I think you can. I think you can just start.
Think about what he.
I'd go in the new one. Yeah, say goodbye, and then we come right back. Thank you, Spiros. That was fantastic.
This guy's name is Guy. He looks like a friend from the meetup.
His name is Guy.
J-A-I.
Who's that guy? Who's that guy? Dun, 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 dun.
This is the.
Alrighty, guys. Have a good night.